How's it going? Today I'm going to show you why there really is no twin paradox. So the twin paradox is kind of like this. We've got a guy who says he's stationary, and then there's another guy in a reference frame that says he's moving. So because there's no acceleration here and there's no acceleration here, they're both inertial. Neither one of them is a preferred reference frame. So he can go, I'm moving, you're stationary. That's from his viewpoint. And then over here, if we look at it from his viewpoint, he can claim equally that he's stationary and you're moving. So we know from special relativity that when one reference frame is moving relative to another, the one that is moving actually has time slow down. So how can time slow down in both reference frames, and how can one say he's stationary and the other one's moving and vice versa? That's the paradox. So in this video today, I'm going to show you that there really is no paradox. And then I'm also going to show you why time slows down with speed. So when we're looking at this paradox here, we have to ask ourselves, what experiment can both of these observers do to confirm they are not moving? And when we do that experiment, they can both use the same experiment to claim they're not moving. But when we look in it in more detail, we're going to see that the actions or the results as the experiment plays out are not the same. But the result is the same, and that's the reason we're running into this paradox. All right, so here's the experiment that both of these observers moving in their respective reference frames can do, and it'll tell them that they're not moving. And this is the reason we get into this paradox, is because they both get the same result of this experiment, but we're going to see that as the experiment plays out, each particular step is actually not the same, comparing one moving to one stationary. So here I am in my box. I'm moving at some velocity v, and this guy is stationary. They can both do this experiment. They're going to emit light in both directions, and we know that the speed of light is constant. And because they're in the middle, the light will go down here and reflect off the respective ends of their boxes. And it takes time, obviously, to go from point A to point B back to point A. So by the time the light comes back to the middle of the boxes, it arrives at the same time. And because the light arrives at the same time in our stationary frame and arrives at the same time in our moving frame, they both can claim that they're not moving. They're both inertial. But we're going to see that the four distinct events that have to happen. So there's the emission of the light. That's our first event where we emit our light. Then there's the reflection or the bounce left side. And then there's the reflection on the right side. And then there is the absorption when it comes back to the middle. And you're going to see that in one of these reference frames, these happen at the exact same time. Then you're going to see in another reference frame where one of these happens before the other one. And when that happens, that's the reference frame that is moving. But we also have to include a third reference frame, and I'll show you what that is. All right, so I got to do an analogy here so that we can understand this as we're talking about this twin paradox. So here's one of the mistakes everybody makes with the twin paradox. They always talk about two reference frames, the stationary guy and the guy who's moving relative to the stationary guy. There's actually three reference frames, and we cannot exclude the third reference frame. So emitting light while you're a body of mass moving through the universe, is very similar or analogous, I think I said that wrong once, to dropping a pebble in a lake while we have our hoverboards. So here's our moving guy, here's our lake, and here's our stationary guy. Notice that there's 3 reference frames here. Moving, stationary, and then my lake. So this is my moving box and this is my stationary box when I'm doing this with light. The lake is analogous to the electromagnetic field that light travels through. So look at it like this. My lake is perfectly flat. This hoverboard is just hovering just an inch or 2 off the top surface of the water. It's not interfering or causing any ripples. And he's hovering just above the lake, but he's stationary relative to the lake. They both are going to drop a rock down in the lake. So how fast these waves go is completely independent of his speed or him being stationary. How fast the waves go from my rock being dropped in the water is a property of the lake. Just like light, when we emit a photon, how fast light moves from that event point is a property of the electromagnetic field. It has nothing to do with his speed or his direction or his speed or his direction. So let's look at this. So I got some sensors on the end of my hoverboards. When a wave hits them, they're going to illuminate. So at 1 second, the waves move out yay far. But now he's moving. So as time is going by and these waves are going out, his center point or his reference frame has moved from where the waves started. This is actually called an event. And an event is an instantaneous point that happens in space and time. Same thing for a photon. When we emit a photon, it's an event point. It doesn't move, it's stationary, and light propagates out at the speed of light from the event point. All right, so 2 seconds go by, my wave has come out to here, my wave has come out to here, and then 3 seconds go by, and the guy who's not moving relative to the lake, obviously if he's not moving to the lake and the waves go at the same speed, it illuminates my light at the same time. But now this guy is moving, and the event point is way back here, and he's moved up to this point right here. So the wave actually hits here first, and let's just say it's right there. So this one will illuminate, and then it's going to take some more time for this wave to catch the front of that. So at some future time, the wave finally hits the end over here and it illuminates. But since he's moved from his event point, the wave that hit back here is now way back here behind him. So again, to reiterate, when we always talk about the twin paradox, we always talk about the guy moving and the guy stationary. We must include the third reference frame, and that's the electromagnetic field that exists throughout space. And both reference frames are moving or being stationary relative to that electromagnetic field, just like he is moving relative to the lake and he is stationary to the lake. All right, so let's kind of reiterate here. What I'm trying to do is show that there are actually 3 reference frames when we talk about the twin paradox. There's the moving reference frame, there's the stationary reference frame, and then in the backdrop is the reservoir of the electromagnetic field. So we can't exclude the electromagnetic field. That's what the light propagates through. So we're trying to compare our moving reference frames when we emit a particle of light from the center of the box. They reflect off the ends and they come back to the absorption point. So there's 4 distinct events going on in both of these reference frames, whether it's moving or not moving. We got the emission. That's going to be where we emit our light from the center of our box. Light's going out both ways. Then we got the reflection off the left side of the box. We got the reflection off the right side of the box, and then the emission and absorption point are basically the same. They're in the center of the box. So then there's our absorption point. So I'm going to show you that one of the reference frames do not have these two events happen simultaneously, but the light always makes it back to the center of both reference frames simultaneously, and that gives you the impression or the illusion that you're not moving. All right, so let's look at this right here. So simultaneity, Einstein said that we cannot conclude with absolute certainty that events happen simultaneously. So in physics, every time you make a statement or an equation, there has to always be a reverse. So it's sort of like this. Here's a marble, and I got a marble right here, and it's moved at 100 miles an hour. It comes over and hits this marble, and they explode. But I can also do it in reverse. I can take this marble and move it this way. So now this one's moving, this one's stationary, and the same outcome happens. So in simultaneity, here's a real simple thought experiment. I've got two guys, one stationary and one moving at velocity v. Their starting point is equal distance from two planets. These two planets emit light at the exact same time, 1 o'clock. And then a minute goes by, so at 1 o'clock, 1 minute, my green guy has moved down. My black guy is still stationary, equal distance between the planets. So here comes my information at the speed of light. Neither one of these guys have any information as to what has happened yet. Then at 1 minute, or 1 o'clock, 2 minutes, the light finally reaches my green guy. So he says that this thing happened at 1 o'clock, 2 minutes. He still hasn't any information that anything happened or any light was emitted from my planets. So another minute goes by, so at 1 o'clock, 3 minutes, the information arrives simultaneously. So he concludes that the light was emitted at the same time from both planets. He's still moving along this way. He still doesn't know what has happened over here. Then some time goes by, 1 o'clock, 4 minutes, the light finally arrives to him. So he concludes that these two events did not happen simultaneously because this information got here at 1 o'clock, 2 minutes, and then this information got here at 1 o'clock, 4 minutes. For him, it did. They happened simultaneously. So the same thing has to happen in reverse. We have to be able to say that. So this is what he concluded. He said two simultaneous events, this and this, arrive at different times. So then he concludes that the events are not simultaneous. So this has to happen in reverse. We have to be able to say that two events not simultaneous have to arrive at a point. Let's call that our guy in the middle of the room right here. So two events not simultaneous can arrive at a point simultaneously, given the illusion that these two events happened at the same time. And this is the key to solving the twin paradox. All right, so again, here's what we're trying to decide is which reference frame, the moving one or the stationary one, will have these events happen at the same time or different times. And we've also talked about how everybody always likes to talk about the stationary reference frame and the moving reference frame. But again, we must include the electromagnetic field that everything exists in. So there's not one absolute electromagnetic field. Every body of mass creates its own shape of space, and therefore every electromagnetic field or reservoir of electromagnetic fields surrounding a body of mass is its own particular reservoir of electromagnetic fields. So we've actually got 3 reference frames. We've got our stationary one, our moving one, and then sitting in the backdrop or the reservoir that everything's moving in or exists in is our electromagnetic field. So here's our stationary guy. We're going to emit our light from the center of our reference frame. Light goes at the same speed in both directions. So it goes from E to L, and then it goes from L to A, or did I get that right? No. Then it goes from L to A. So the total distance is E to L, L to A. And since it's the same distance over here, it goes from E to R and then R to A. So this travel time for light and this travel time for light, because they cover the same exact distances, arrives back at my absorption point at the exact same time. He concludes this, that both these events are simultaneous events, the reflection times. So EL, time and distance, equals LA, ERR. So all these equal. But now let's go and look at our guy that's moving. So remember back to where I did the analogy where I showed that emitting light in a moving reference frame is very much like a hoverboard going over a stationary lake. Once you drop that rock in the lake, how fast those waves move from where the rock hit the lake is a property of the lake. It has nothing to do with this moving reference frame anymore. Light is the exact same way. So when I am moving, and I'm moving relative to the electromagnetic field in the background, how fast the light moves from the emission point or the event is dependent on the electromagnetic field. It has nothing to do with the reference frame that excited the electromagnetic field or created that emission point of light. So as he is moving in this direction at some velocity v, he's going to be moving relative to his emission point. So here we are at t equals 0 seconds. I emit my light, it's going both directions. I'm equal distance from the left and the right side. So now it takes time for the light to go from A to B. And during that time, my reference frame is moving relative to my emission point. So this distance right here is actually shrinking, and then it's conversely different or opposite on the other side. So as this is trying to go from its emission point to the right-hand side, this distance is increasing. But because nothing's faster than light, this will eventually make it to the right side of my moving reference frame. So at t equals 2 seconds, you can see that the center of my box, which is now my absorption point, has moved relative to my event point. But the amount of light that has gone from my event point over here and reflected off the left side, if we were to add all that up, it's the exact same amount of light or distance of light from here to here. So you can see that this event happens first. So in a moving frame, this event happens first. And this light starts coming back. Now, because the reference frame is still moving away from the emission point, this light is trying to catch up. So this distance right here changes, and the absorption point is moving away from the light, but again, the light's faster, so it eventually will catch up. Then at 3 seconds, I finally reflect off the right side of my box. So then this one happens next. And the light now is coming back towards my absorption point. So this is moving towards the light as the light goes that way. So the distance is kind of actually shrinking faster on this side, and it's growing a little bit on this side, but the speed of light always wins. So with all that in consideration, this happens. The light eventually makes it back to the center of the box, and they arrive at the exact same time. This guy gives a conclusion that he is not moving. So remember earlier where I showed you that 2 simultaneous events can be not simultaneous to an observer because he's moving. So now I'm showing you where 2 simultaneous events, where 2 non-simultaneous events can be viewed as simultaneous. So this one and this one happened at different times, but they got back here at the same time, so he concluded he wasn't moving. when in fact he is, because this event happened at 2 seconds and this event happened at 3 seconds. So that's the reason we always have a problem with our twin paradox. It's because one, we don't ever include the third or the preferred reference frame, that's the electromagnetic field. And two, we conclude that because the light arrives at the same time, it must have hit at the same time. It didn't. So that's why there's no twin paradox. The reference frame that's moving relative to the backdrop of the electromagnetic field is the guy that is always moving relative to the guy who has EL plus LA, ER plus RA. When these two equal, and then all these distances, E to L, LA, and E to R, R to A, when they all have the same distance in the same time component, you're not moving. But then down here, we can see that E to L plus L to A equals E to R plus R to A. So E to R and then R back to A. However, E to L, this one right here, is less than L to A. So this distance that light travels to hit the box and reflect is actually smaller than it is for the light to hit the box here and go to here. Same thing on the other side. R back to A is always less than E to R. But E to L is the same as R to A. And then LA, so L to A, is the same as E to R. So these two are equal and these two are equal. But EL does not equal LA. And then ER does not equal RA. And that's how we can tell that this guy is always moving relative to this one. So his time rate will always be slower than his time rate because he's the one moving relative to the electromagnetic field that permeates through the backdrop of both reference frames. All right, so now let me show you why time slows down with movement. Here is the reason time slows down for a moving reference frame. And again, I want to stress that you got to try and remember the analogy where we've got the hoverboard moving over a stationary lake and we drop the rock down into the water and the hoverboard moves away from the point where the rock entered the water. So dropping a rock from a moving hoverboard into a stationary lake is analogous or very similar to us having a moving reference frame and emitting a photon of light. The light travels at the speed of light relative to its emission points at the same speed in all directions. And we always got to remember that we don't exist in a vacuum. Light doesn't travel through empty or free space. It's actually a wave in the medium of the electromagnetic field. So anytime we talk about a reference frame, we've always got to remember that in the background or in the backdrop of those reference frames is the electromagnetic field. We could be moving with it at the same speed, like Earth and its respective gravity field going around the sun. We could be right on the Earth, moving at the same speed as that moving reservoir of electromagnetic field. So when it comes to movement, there's only one way to increase the elapsed time between 2 points, and that's to increase the distance. So distance equals rate times time. Because we know our rate is the speed of light or light, it becomes a constant. So if we want to increase the elapsed time from point A to point B, we have to increase its distance without changing the shape of our reference frame. So obviously the elapsed time here would increase if we doubled our distance. So here's a stationary frame and here's a moving frame at some velocity v. We're going to emit light from the left side of the box at the exact same time. So remember, it takes time to go from point A to point B. And during that time, my reference frame that emitted the light is going to move. So the finish line right here, while this is trying to catch up to it, is actually moving away. My emission point is an event. It happens at a specific point and place in my reservoir of electromagnetic field. It does not move. So the speed of light travels from my emission point at the speed of light. I can also move relative to my reference point, my event point where I emitted the light. And you can see that this distance for the light to travel in a stationary frame is x. And the distance, we've got the same starting line, but then the finish line is over here. And you can see that this distance for the light to go from point A to point B increased relative to this one for the simple fact that it was moving relative to the emission point.